So when we're dividing radicals, it's fairly simple. It's not like long division or synthetic division stuff when we were dealing with polynomials. Most of it is simplifying, and it's just knowing the rules of simplifying when we've got a radical. And so if we're looking at it in terms of steps, we would say, let's go steps. Step one would be to divide the coefficients. Right? Does anyone know what coefficients are? Not really. Okay, I'll go over it. You guys should know this one by now, but I also know how easy it is to forget stuff. And then use the quotient rule. Now, the quotient rule I don't expect you to know, but I'm going to explain it to you. Quotient rule. Right? The quotient rule is if I have, say, something with an index of like n, it could be anything, right? That could be a square root, it could be 3, it could be 4, it could be 5, doesn't matter. If I have a fraction under it, I could rewrite that as the n root of a over the n root of b. So I could separate the numerator and the denominator, right? That's all the quotient rule is. A coefficient is if I have 3x squared plus 2x, my coefficients are 3 and 2. Right? They're those numbers that are in front of or being multiplied to from a variable. But also if I have like 3 rad 3 over 4 rad 3, 3 and 4 would still be considered the coefficients. Does that make some sense? All right. So rule number 2, I guess I can get rid of this stuff right here. We'll say rule number 2 or step number 2 is just to simplify the resulting radical. Sometimes that's the hardest part. So those are the only 2 steps we've got. I would rather use the time showing you how to do problems than explaining a bunch, and just explain as I solve the problems, because I think that will do you a little bit more good. So I'm going to start with the first example because, well, it would be stupid for me to start with the 7th example. If I have 12 times the square root of 160 over 2 times the square root of 5, the first thing it says is to divide the coefficients and then apply the quotient rule, right? And so I'm going to say 12 divided by 2. Those are my coefficients, right? If I have 12 on top, we can say that that's 12 divided by 2, and that is going to equal 6. And if I think about this in terms of the quotient rule, that's like saying I have 160 over 5. So 160 over 5 is the same as saying 160 divided by 5, right? And if I did go out and divide that, I would wind up with 6 times the square root of 32, because 160 divided by 5 is the square root of 32. Now, we have taken step 1 as far as it can go, right? But step 2 says we have to simplify the resulting radical. And this 32, not as small as it can get, right? If I look at 32, I know that it is 2 times 16. And we know that 16 is a perfect square, right? It's 4 times 4, which means I could pull a 4 out. So here, technically, I would have 6 times 4, and this 2 would have to go back under. So I would get 24 times the square root of 2. Make a little bit of sense? Seeing yeses? All right. If I have a similar problem, but say it's all, my favorite kind of problems actually when we're dealing with anything simplifying as far as division of fractions or divisions of square roots of radicals, are always anything with just variables, because I think they're the easiest problems to do. For example, if I have the square root of x cubed times y to the 9th over the square root of x squared y to the 5th, right? If I apply the quotient rule, I could rewrite that whole thing, right, as x cubed y to the 9th over x squared y to the 5th. And do you guys remember, we can reduce these, right? I can look at these and I can go, okay, well, here, let's write the square root here. Here I have x to the 3rd, and here I have x squared. So here I have 3 x's, and here I have 2, right? So I can divide it by 2 x's, right? I could cancel this x squared and 2 of these, and I'd be left with x. Does that make sense? I had 3 x's on top. I had 2 x's on the bottom, so I could cancel out 2 from each. Think of it as factoring. And I would wind up with x underneath, right? Here I have y to the 9th, and here I have y to the 5th. So I can cross out 5 x's from here. 5 y's from here, but I could also get rid of 5 from there. So 9 minus 5, I would have 4 y's left. Did that make sense? Because I feel like once you get the hang of these, they become the easiest thing for you to do. I feel like they're easier than actual numbers. That one's pretty similar. It's just got 2 numbers in it. Let's do this one just because it's got a cube root and we haven't seen anything with cube roots yet. And then I'll do a couple of the more complex ones where you have to rationalize the denominator. So we're looking at 3 more problems and then we're done. All right. So if I have the cube root of 7x to the 5th over 64y to the 6th. 64y to the 6th. So keep in mind, this is a cube root. I could rewrite this as the cube root of 7x to the 5th. The reason I'm separating them is because there is nothing in common on the top to the bottom. 64 is not divisible by 7. Up here I have x's. I don't have any y's. So I'm just going to separate them now and do them as separate pieces, right? I could still break them down underneath if I want. I just find it easier to do this way since they already have nothing in common. Now, if I look at the cube root of 7, nothing times itself, right, is going to equal 7. So we're going to keep that 7 underneath. Here I have x to the 5th, though, and this is a cube root. So for every 3 x's that I have, I can pull 1 out. Here I have 5. So if I go 5 minus 3 or 5 divided by 3, I can only pull 1 x out, right? And I would still have 2 x's left. So here I'm going to have x squared left. And then we're going to fix what it tried to fix for me. So that takes care of our top. There's nothing else I can do to that, right? It's as small as it's going to get. I can't pull a cube of anything out of that now, right? I can't pull 3 of anything else out. If we look at 64, well, what do I know about 64? It's 2 times 32, right? Which is 2 times 16, which is 2 times 8, which is 2 times 4, which is 2 times 2. So it's 2 times 2 times 2 times 2 times 2 times 2. If I look at that, that's 2 to the 6th power, right? That's 6 twos. For every 2, I can pull one out. So there's one. There's another one, right? So 2 times 2 is 4, and I could pull that whole thing out. There's nothing left to put under there number-wise, right? We've used up all of that 64. If I go 2 times 2 times 2 times 2 times 2 times 2, I'm going to get 64. We've pulled it all out. Now we've got y to the 6th. For every 3, I can pull one out. 6 divided by 3 gives me y squared. There's nothing left under the radical. So this is our final answer. And these are kind of basic, right? Like you could kind of figure these out. Anytime I have 3 of something, I could pull it out. If I have more than one set of 3 of something, like in this one we had 2 sets, well, you can pull out 2 of them then. They're not always going to work out that well because if you remember, we can't have a radical in a denominator, right? So if I have, say, 3 over 2 times the square root of 5, I can't really reduce anything on this problem, but I can't leave that radical 5 in the denominator. So I'd have to do what we call rationalizing the denominator. When it's just something like this, something multiplied to a radical, we can just multiply it times the radical over itself, right? Square root of 5 over the square root of 5. Because when I multiply the square root of 5 times the square root of 5, I get 5, right? And so this would be 3 radical 5 over 2 times 5, which is 3 radical 5 over 10. So not too hard when you've got a single one working like that, but sometimes you don't have a multiplication in there. Sometimes you wind up having something that you can't just where you have to, if you remember back to when we did complex numbers and we would have to multiply by a complex conjugate, if you have something of the variety, if I have 4 over 4 plus the square root of 2, right? So I have something like this. I can't just multiply this times the square root of 2 over the square root of 2. Doesn't work because that 4 plus the square root of 2 is one entity, right? I can't factor something out that I'm not able to factor out of both pieces. So what we have to do with this is we would put this in parentheses and we would multiply by what we call the complex conjugate. Well, in this case, it would just be the conjugate. So if this is 4 plus radical 2, we would multiply times 4 minus radical 2 over 4 minus radical 2. Same thing on both of them because that's the same as multiplying times 1, right? And we are just going to have to distribute. So this 4 would get multiplied times this 4, and we would have 16. And here I would multiply 4 times negative radical 2, and I'd have negative 4 times radical 2. Now this piece, when I multiply these together, I kind of do them as side work so that I don't have to keep writing the equals, the numerator over and over again. I just do this as a little bit of side work and I write it, then I fill it in over here. But this is just like when we were multiplying binomials before when we had variables. We would take each piece. So we would take this and we would multiply it by each piece of this one. So I have 4 times 4 is 16. And then I'd have 4 times negative radical 2, and I'd have negative 4 radical 2. Now that I've multiplied this 4 times everything over here, I'm going to start multiplying this radical 2 by every piece over here. So I'd have 2 times radical 2 times 4, which is plus 4 radical 2. And then I'd have radical 2 times negative radical 2. And when I multiply a radical times itself, I just get what's underneath it. And if you look at this, you can see why we choose the conjugate. Because here I have 16. Well, I have minus 4 radical 2 plus 4 radical 2. And that part just equals 0. So I wind up with 16 minus 2, which equals 14. And so what we put under here is that 14. And that I wish was enough, but it is not quite enough. Everything here is divisible by 2, so I need to at least reduce this fraction. So that would become 8 minus 2 rad 2 over 7. So suppose you got to here on your homework, right? You'd get almost full credit for that, right? Even on a test, I'd give you almost full credit for that. That's the whole point of being able to show your work, right? Is that I can give you partial credit. But the true answer would be to simplify it all the way. Any questions about any of that? The homework that you're getting is a worksheet where you're going to have to show work. Again, this is recorded, so you could go back and look at any of the examples. There are 17 problems on your homework, but you only have to do the odd numbered ones. So keep that in mind when you're looking at it. Don't feel overwhelmed by the fact that there are 17, actually 18 problems on there. You only have to do the odd. So there's really only 9 problems. Most of them are of this upper variety. And I think there's only like 2, like that last example, that might fall into that category. I'm looking because I have the homework right here in front of me. Yeah, there's only 2 that fall into that category. So if you don't have any questions, I will stop the video.